Okay, in the previous chapter, chapter 6, we learned a lot about entropy, about free energy, and how forces can be related to free energy. Specifically, we showed that a force, for example, an entropic force, like osmosis or something like that, could be found by taking the negative of the derivative of the free energy with respect to some displacement, some length. Okay, and this is reminiscent of a more general definition of a force as the negative of the derivative of a potential energy, any potential energy with respect to a displacement. Okay, reminding that a free energy is equal to the energy, which could include all sorts of stuff: kinetic energy, potential energies. You could even include ideas of work when you have combined systems, or a system that has two parts, one doing work on the other. You can consider that a potential energy and write it as a force times a displacement. And then here's the entropic term. So TS is units of energy. And the important thing in a spontaneous interaction is that the free energy of that system, if isolated, must go down. Okay? All right. Then we found that the free energy can be related to this thing called the partition function, which is a probabilistic expression. It describes the probability of all the possible states. In fact, this is a summation of over all the states, that's what the S is for, of the Boltzmann factors for the energy of that state, divided by the thermal energy. And so Boltzmann factors describe what are the probability of being in a state with a certain energy, and then the partition function just says sum over all those possibilities. So this is just totally a probabilistic thing. But from it, we get an energy-like quantity, which is related to very real quantities that we can measure macroscopically. And then we could find forces. So these are the source of entropic forces. So we're going to try and play with this a little bit and try and understand how can we do some of the mathematics. And so this is kind of reviewing sections 7.1.1 and 1.2. Okay, so to start, let's talk about the ideal gas law. We love the ideal gas law. It's something that we measure macroscopically, and we have seen it derived from microscopic and probabilistic principles. So what we're going to say is, okay, this should be true no matter how we get to it, via probability, via kinematics and Newton's laws, or via free energy. And so the question is, can we find pressure as a derivative of free energy with respect to something? And if you look back at our previous relationship, force is the negative derivative of free energy with respect to a length. And so if we just divide F by A, and therefore putting an A down here, that is the same thing as pressure and volume. And so it seems reasonable just by multiplying some constant area A, or divided by a constant area A to either side, that this should be a way of finding pressure. So let's check that with our definition of free energy and the equipartition function. Or sorry, not the partition function, not equipartition function. Okay, so we kind of take it. Oh, sorry, I guess I show it right here. And so let's take this derivative first. Let's insert what we know for F. And so this negative sign carries from this definition. And then we plug in what we know for F, which is a negative kBt times the natural log of z. By the chain rule, net derivative of a natural log of z would give me 1 over z times the derivative of z with respect to v. And then I lost the minus sign because I had two minuses. So there's two minuses here, gave me overall positive. So now I need to figure out what the derivative of z with respect to v is, and I need to know what z is to start. So let's figure out what z is. Okay. So remembering that z is a way of counting all possible states. All states. Okay, we have to sum over all possible states. So of the Boltzmann factors. So the Boltzmann factors in this case, if we're looking at a box of gas molecules, each with mass m, Okay, they could have a range of momentum. So particle 1 will have a range of momentum. So I have to integrate, that's what this integration is adding up all the momentum that particle 1 can have. So that's the integration variable, dp1. What are all the possible momenta it can have? Okay, and then I have to do it again for the second particle. And I've got some dots here to say I've got to keep on going. Okay, now this could have a certain momentum at some location in the box, and it could have that same momentum at a different location in the box. And so the total number of ways of arranging those molecules to have that momenta, therefore that energy, also depends on how much space the box has, or how much space is available for the particle to move around in. And so in order to truly count all the possible states, I also need to count the space available per molecule. So V2 would be the volume of particle 2, some small amount of volume surrounding the particle, and it could be anywhere in the box. So I have to integrate over the whole box volume. But this is just a number. This just gives me V. And I do it for 1, and I do it for ... for all the particles, so n particles. This constant out front takes care of some other things. Maybe there's some potential energy due to gravity, but it's going to be constant throughout the whole system. And what I really care about in this is how does Z depend on V? Because I ultimately have to take the derivative of Z with respect to V. And so anything else is just a constant with respect to V, so I'm not too worried about it. So I can group a bunch of things that are independent of V into this constant, like some potential energies or something like that. So now that I've looked at this whole complicated thing, including those 3 dots right there, which mean these momentum integrals go for all n particles, okay, now I need to just kind of understand I technically have to do those integrals. These ones I can do easy. An integral of dv over v is just v, and I have n of them, so I have v to the n. Okay, the integral of this, well, that's harder. It's something, but if you notice, it has nothing to do with volume. So this will give me a number, and volume won't be in it. So it's a constant with respect to volume. So I can just take that and plug it into this constant. So this constant here is some different constant than it was before. And that would be the same for all of these momentum terms. And so I ultimately end up with, in terms of V, a constant with respect to V. It may have a whole bunch of other stuff in it, but it's a constant with respect to V times V to the n. And so though this was pretty complicated to think about, it ended up being fairly simple to actually quantify. So with our equation for Z as a function of V and n, we now have the derivative, which is simply by a power law. We'd have NCV to the n minus 1. Okay, so remember we did that so we could find the free energy and then take the derivative of free energy. Allowed us to do that chain rule on this. So this is really what we were trying to find. Okay, so now I plug it in. The dz dv is ncv to the n minus 1. Z is cv to the n. So the constants cancel. Again, that's the beauty of working with partition functions, is because you will always have a z down below and then some function of z above, any constants will cancel out. Okay. Now I have n minus 1 factors of v above and n factors below, so I have one more factor of n or v below, and so I'm going to be left so that all the others will cancel, and I'm just supposed to n over v, and so this is my end result. So remembering that it was kBt times this stuff, now that I know what that stuff reduces to, I recover the ideal gas law. Pressure is equal to kBt times that stuff, which ended up being n over v, and that's just the ideal gas law. So this probabilistic picture recovered our familiar and well proven form of the ideal gas law. So that should give us some confidence in the ideas of free energy, derivatives of the free energy, giving us entropic forces, and how to use the partition function. Now you can do that again, and section 7.1.2 says, hey, let's try and look at derivatives of the free energy with respect to pressure, well, that ought to give us our average volume. So if we allow the pressure to be constant, and so some piston can fluctuate under this constant pressure, then what would be the average volume? Okay, and so we'd consider small fluctuations in pressure around some constant value. Okay, and so the section 2 does it a little differently, considering probabilities. So if you remember way back, we defined the average value of something as being that value times the probability of that value summed over all possible states of that value. So this is how we would represent it. Now that was very general, just a statistical way of considering what is an average value. But remembering that the probability of anything, as we saw in Chapter 6, is related to the partition function. It would be the Boltzmann factor for that one state divided by the partition function. And so doing this, you'd end up getting something very similar to what, or a similar process to what we did for the pressure being a derivative of the free energy. And so I won't do the mathematics on that one, but it's just another example. And so what we do pull out is that the free energy, derivatives of the free energy with respect to certain parameters, allow us to find other parameters. And the big problem is just finding the partition function. So that is section 7.1 complete, 7.11 and 7.12.